Hello, welcome again to our tutorials on the voltage regulator circuit. So as you can see right on your screen, there is a voltage regulator circuit analysis of which we have seen in our previous discussion module. I have analyzed this circuit theoretically and provided you detailed equations for the voltages and the currents into the circuit, and I have explained how this circuit will maintain a constant voltage across the load despite variations into the load that may happen due to various reasons. For example, noise, some disturbances like temperature variations or varying load conditions, and it will also maintain the constant output voltage despite some variations into the input side. And the reason for this circuit to maintain the constant output voltage right here is the combination of this zener diode and this series pass transistor. So what is happening here is that you have an input voltage source, which is unregulated supply voltage, and you have a series resistance R1. And as soon as your input voltage is greater than or equal to the zener breakdown voltage, there is a current flowing through the zener. Also, the same current goes to the transistor, and actually the voltage drop across this junction, which is VBE, is modulated, is changed if there are changes into the load. And once that control voltage VB is modulated, the base current is modulated, and subsequently the load current that flows into the load modulated. So please refer to the previous video. Link is in the description box and you will see the complete operation. But now what are we going to do in this module? We are going to simulate the circuit for variations into two things. First is the load, and the second is in the input supply voltage. So let's say your supply voltage, which is fixed at 10 volt, varies. It has variations. It is not, because that's why we call it as unregulated voltage. So there is a variation. It may vary from 10 volt to 15 volt or something like that. So see the design values of 1K, load is 10K. Diode has a breakdown of, let's see how much is the breakdown we have chosen for the diode. So right click here and we see we have a zener diode of 6.2 volt of breakdown. This is the diode number. A manufacturer is on semiconductor. So we see that. So 10 volt is greater than 6.2 volts. So this diode gets into the conduction. It is in the reverse bias. Similarly, transistor, right click. It's a simple NPN transistor. If you want to pick a new transistor, click here, and we have chosen this 2N222. So it has, these are the specifications, like voltage drop across collector to emitter is maximum 30 volt, maximum 800 milliampere collector current it can withstand. And there is this beta F is the DC current gain, which is 200. So if the base current to this transistor is, let's say, 1 milliampere, so the collector current would be 200 times higher, that is 200 milliampere. So that's how this circuit will work. So now what we're going to do is we are going to vary this voltage source, and we see if still there is the output voltage constantly maintained or not. And what is the output voltage? Do you remember from the previous section? The output voltage is V naught, which is equal to Vz minus VBE. So we have seen that theoretically that the voltage across the load will always be zener diode breakdown voltage minus one drop of the junction voltage across the base and the emitter of this NPN transistor. So 6.2 volt minus 0.7, approximately 5.5 volt. So we have seen that in previous model. So refer to that. So we have to check now if that voltage will constantly be maintained here or not, if there are variations in the input side. So what we would do here, we run an analysis. We go to simulate, we go to control panel, not the control panel, simulate, edit simulation command, and we are here. So before that, let me erase all these notations over here, clear the drawing. I go to edit simulation command, and now there are many analysis I can perform on this circuit. So this is a spice. You are also learning spice here. So what I choose the DC operating point. We have done that in the previous model. So it gives you all voltages and currents in the circuit. Go to DC transfer. No, we want DC sweep. So this analysis will compute the DC operating point of this circuit, while it will step the independent sources like the input supply voltage here, 10 volt of unregulated supply. It will step that voltage. Okay, so name of that first source to sweep is, what is the name? Here, V1. So we will write V1. And what kind of sweep you want? Click here. I want linear sweep. So I choose start value is, let's say, 10 volt. It is now 10 volt. I want to go to 15 volt. So let's say there is a variations from 10 to 15 volt. That much fluctuation or deviation is happening. Usually in practical case, it won't be that high, maybe if you just couple of volts, but we'll just see that. And let's say the increment is 0.1, no, 0.5. So I am stepping up this input voltage source from 10 volt up to 15 volt with the steps of or increment of 0.5 volts. So I'll start from 10, then 10.5, then 11, 11.5, 12, and so on up to 15. So look, as soon as I input these parameters here, I have a syntax ready for the spice command, which is .dc v1 stepping from 10 volt to 15 volt and up to, 0.5 is the increment. So I click OK. This command is ready. I can use my mouse to place it somewhere on the screen. Then I press space bar on my keyboard, and you see the circuit is in the middle of the screen now. So I am ready to simulate this circuit. So I click here, the running man. So I click and see I got this waveform window open, where I see on the y-axis. On the y-axis, I don't have anything, but on the x-axis, I see some reading like 10 volt to 15 volt. That is what my sweeping is. So what I can do here, I see on the bottom screen, I have this red probe automatically hovering over the screen. So it is helping me to probe the voltage at the node I want. So this is the node I want. This is the node I want, for example. So I choose first input. So I click here with the right click on the mouse. I see now the voltage at node N001, which is this node, gives me a voltage that varies from 10 volt to 15 volt. So this is linear sweep I am doing. Now I want to see the output voltage. So I will see, I click here, and the blue is the V of V out. So that's the output voltage at the node V out. I have labeled this net here. Okay, we have described this in the previous session. So you see now, if there are variations in the input from 10 volt to 15 volt, I have the variations. Remember, the output voltage is Vz minus VBE, which is about 5.5 volt in theory. And it gives me precisely that and it is throughout the range, it is constant. However, if we look it in a separate window, we can see that it will have some variations. And how much is that variation depends on your circuit values and other parameters. So what I do in the waveform, I right click and then I choose add trace. So these are the different currents and voltages I can do. But again, I right click and I choose add plot pane. So I click here and I want to analyze input and output in two separate windows. So I do one thing, I click here, I hold the mouse button and take it up. Now I see the green is my input and the blue is my output. And the output is varying from 5.66 to 5.73. So there is about zero point 0.7 volt drop, zero point 0.7 volt difference if I am varying the source. If my input voltage is increasing, the output voltage is also increasing, and the output voltage is about maximum is 5.7 volt. Okay, so this is how. So it's not exactly constant. You still have a difference of about 0 0.7 volt in the output. Okay. Now, what if I just come back to the window in the schematic and I right click this command that .dc, and here I sweep from 10 volt to 15 volt, but now this time I want to sweep back from 10 to only 5 volt, or let's say 3 volt, and increment is the same. Then I click OK and I click simulate. Now look at the behavior of this circuit. I have green is the input, which is dropping from 10 volt to down to 3 volt. And the output is 5.7 volt initially. It is almost constant till the zener drop breakdown voltage of zener, that is 6.2 volt. It is constant. But after that, the output is dropping to lower value, and minimum it goes up to 2.1 volt. Why is that happening? Because as long as your input voltage in the screen down is equal to or greater than zener breakdown voltage, as we saw in the theory, the output voltage will be maintained constant across the load. However, if the input falls below the breakdown voltage of zener, which is the case we see in the waveform, the output zener is no longer in the reverse breakdown region, and the current flows through the zener start decreasing, and eventually zener comes out of the breakdown. Therefore, it turns off and your voltage is subsequently dropping here. Okay, so we have seen what happens when there are variations in the input, and we have seen what happens, how the output is regulated. Okay, for the increment of the input voltage, we see that the output voltage is not precisely maintained constant, but for the decrement of the input voltage up to zener voltage, we see that output voltage is maintained pretty constant, like 5.7, and it's almost 5.7. Okay. So we saw that. Okay, now in the second section of the same circuit, you see this is an example circuit where we are trying to sweep the value of the resistor. We are stepping the value of the resistor R2. So this is the syntax. We write this command dot step param, because this is the parameter we are stepping. The name of the param is x, and the value we want to sweep is from 1k to 2k at the increment of 0.1k. So we'll run this analysis on our circuit. So we come back Okay, so what we'll do is that we'll click the spice directive and we'll type that command. So it is like dot step param and then x, because we have taken x as a name, and then we'll vary the value 10k. Let's say it goes from 10k to 15k at the increment of 0.1k, that is 100 ohm, and we click OK. And now we'll just do right here. We don't want DC sweep along with your step at a time, one sweep. So we just cut here, save it. And now you see, you got this input voltage source set to 10 volt. Resistors R1 is 1K, diode and transistors are in place, but now load is varying. And the variation is from 10K to 15K at the increment of 100 ohms. So we'll start from 10K, then 10K plus 100 ohm, and 10K plus 200 ohm up to 15K. Let's increase the increment a bit. 10K is too small, let's say 0.5K. That's okay. What we can now do is we want to run some analysis. So while executing that analysis, the spice will step this parameter x and print or plot those voltages or currents you want. So click simulation button, edit simulation command, and here we choose the DC operating point analysis. So click OK. We are placing this command here, and boom, we click run. So you see now we got to monitor our output when there are variations in the load. So click V out, and here we are. So the output varies from 5.66 volt up to 5.674 volt. So it just very minute drop, about 0.1 volt if the load varies from 10K to 15K. So pretty much. So let's say if there is a less variations, let's say it varies from 10K to 12K only, and the increment is 0.1K. Save, run again. And now you see the variations is so minute, that is 5.663 to 5.668. So it just few millivolts variations here. Okay, so you can actually do all bit of stuffs from here. Add plot pane, we have seen that. Then add trace if you want to see other voltages. For example, this no voltage at node 001, voltage at node 002, current through the diode, current through resistor, current through R, current through voltage source, base current, collector current, emitter current, and so many other parameters that you can plot. For example, I want to see the zener diode drop. So I click and it's constant 6.2 volt, which is 6.3 volt actually. Let me zoom this portion. It is about 6.3 volts. So I right click and zoom to fit. So you see now, just add plot pen, and I want to take this zener drop on the other axis. So you see now it is still maintained as a constant. What if I want to plot the input voltage? So input voltage is constant 10 volt because we are not variation. So you see now we have seen if there are variations in the load, we are able to maintain a reasonably constant voltage drop across the load, even if there are variations. What if the value of load falls from 10K to, let's say, 8K? It is falling down. So, or maybe even 7K. We'll see now, and save, and we'll just go on. Now, look at the output voltage in the green. Again, 5.653 to 5.664, just millivolt variation. That's it. It is not dropping like this. Okay. So that's all. So we have seen the variations in the load. We have seen the variations in the input and impact of these two cases on the output. Output is reasonably maintained constant. What if you just close this window and then let's say you run again, and you can plot the currents also. So just see, if I take the mouse on the component, I get the current. For example, it is plotting me a current from anode to cathode of a diode, and that's the current. ID1 is 3.6928 milliampere to 6.3941 milliampere, nearly constant. Don't go by the slope. If you basically take the slope of this curve, it would be nearly constant. Okay, and you are varying the resistance on the x-axis from 7K to 10K. Similarly, what about I come back to screen and you see this is the load current or emitter current. Similarly, can I plot the base current here? Yes, there is a base current, or just right click on this waveform window, add trace, and just IBQ1, that is the base current. So all these things you can plot. So, okay, I hope you understand this comprehensive analysis of the voltage regulator circuit, and it will be useful. So stay tuned.